And when we talk about the dye instability, we mean the heat of hydrogenation. So basically, your professor is going to ask you to compare different compounds with different pi bonds in them, and they'll ask you if this compound is more stable, and if so, does it exhibit a higher heat of hydrogenation or a lower heat of hydrogenation. So basically, you're going to have to compare the different compounds in regards to heat of hydrogenation. So what is heat of hydrogenation? Heat of hydrogenation is the susceptibility of a compound to undergo a reaction where it brings in two hydrogens on the alkene bond. So this bond breaks and it becomes this bond structure. Here was the pi bond, and then these two hydrogens add into that pi bond and end up removing it. So that's the heat of hydrogenation, the susceptibility of a compound to undergo hydrogenation along its pi bond. Usually, you'll see that the more stable the compound, the less likely it will have it will undergo heat of hydrogenation. So, yeah. For example, you have an aromatic compound, and we know that aromatic compounds are very stable. So it's less likely for one of their pi bonds to get two hydrogens added to it, and it basically being removed from the aromatic, because that decreases the stability. And aromatic compounds are extremely stable, so they don't want to change from that stable state to a very less stable state. So let's do an example together. If you're being asked to rank the compounds in regards to heat of hydrogenation, the way you would approach this problem is, first you have to look at the number of alkenes. When you have two compounds that have the same number of alkenes, then you will look at the type of diene. And if you have the two compounds with the same type of diene, then you will compare the substitution of each. And if you have two compounds that are equally the same way substituted, then you'll decide whether they're cis or trans. And using the cis or trans notation, you'll decide on regards to stability. And the more stable, the less heat of hydrogenation it will exhibit. The less stable, the more heat of hydrogenation the compound will exhibit. Okay, so let's go ahead and get started. So first, let's count the number of pi bonds. So in compound A, we have 1 pi bond, 2 pi bonds, and 3 pi bonds. So in compound A, we have 3 pi bonds. Compound B, we have 1 pi bond, 2 pi bonds. In compound B, we have what? 2 pi bonds. In compound C, we have 1, 2, 3, 4 pi bonds, or alkenes. So yeah, let's decide on the ranking. So which one has the more alkene bonds? Compound A, compound B, or compound C? In the case of this example, it seems like compound C has a more alkene bonds, so it will have the highest heat of hydrogenation. Which one has more, compound A or compound B? In the case of this example, again, compound A has compound A has 3 alkene bonds, so it has more alkene bonds than compound B, so it will have a higher heat of hydrogenation. And then lastly, compound B. If you have a compound like this one, you'll compare both of these have 3 alkene bonds, but which one's more stable, or which one will exhibit the least amount of heat hydrogenation? For that, we have to decide on whether the compound is a cumulated diene, isolated, or conjugated. So right away, we can cancel the cumulated diene, because remember, cumulated, the pi bonds are adjacent or they're next to each other. But in this compound, they're separated by 1 or 2 or more sigma bonds. So cumulated is definitely not it. So we either have isolated or conjugated. Let's see. This one is conjugated because the pi bonds are separated by 1 sigma bond each. So it's conjugated. This one has 2. The first one is conjugated, and the second one is isolated. So which one will win? Which one will have the lower heat of hydrogenation? So in this case, it would be compound A, because compound B is less stable because it does not exhibit a continuous overlapping of p orbitals. As you can see, these overlap, but then these don't overlap with these. So this one would be less stable than this one, where all of its atoms have overlapping p orbitals. So compound B will have a higher heat of hydrogenation than compound A. So yeah, that's about dye instability. That's a trend. You can screenshot this if you would like, because this is helpful in ruling out and deciding which alkene is more stable, or which diene or conjugated, which system or compound is exhibiting the higher stability and hence the lower heat of hydrogenation, and which compound is exhibiting the more heat of hydrogenation and so the lower stability. And yeah, this is crucial to know, so memorize these rules and you'll be okay.